Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today begins our final topic in calculus. We're going to cover it over a couple of lessons because there's a couple different variations of it, but it's called the washer method. And it's a technique designed for finding the volume of solids when we revolve around, a certain axis, but it's a technique that we use when our solids look a little different than they have the last couple of lessons. We can't just apply the disk method here because our solids are a little bit more complicated. So let's jump into a problem and kind of show you what we mean by showing you a visual of what these different solids are going to look like. So it says region R in the first quadrant is enclosed by the y-axis, the line y equals 4, and the curve y equals x squared. We need to find the volume of the solid generated when R is rotated about the x-axis. We're going to give an exact answer in terms of pi. So first thing to just kind of note, we're revolving around the x-axis, so our integral should be in terms of x, not y. And if it says give an exact answer in terms of pi, it means we're going to be doing this completely by hand, no calculator. What I would encourage you to do is pause the video and see if you can kind of visualize this on your own. Maybe you want to sketch some cross sections to kind of help you get an idea. But and you may not, right? You may get confused, but I kind of want you to explore this before I just kind of show you exactly what it looks like. So pause the video, see if you can draw a couple of cross sections here, and try to figure out what this solid is actually going to look like. Okay, so something you may have been tempted to do, and I'm just going to do that first, is start by picking points on this blue curve and rotating them. Oh, that was pretty poor, wasn't it? Let's try that again. Whoops. And rotating them around the x-axis. You may have seen this little top-looking figure, right? Now the problem is that doesn't represent the region R when it's rotated around. That represents this region right here, right? This green region. If I rotated this green region around, that's what would give me this little top-shaped figure. Region R is actually a little bit more complicated. Let me erase this. Now you may have thought, okay, well, region R, maybe you start out by drawing this cylinder right here. Maybe you just start with the purple line. So you have a cylinder. Now the problem is, obviously region R is not going to create a cylinder for us either. What happens though is it's actually a combination of the two solids that I just drew. So it's actually this cylinder, and then we need to remove this little top figure that we drew originally. This is a little hard to visualize. I'm going to break it down for you even better in a second. But essentially, if I took the entire cylinder and then I removed this top half, or not the top half, but this top piece of it, that would give us the volume when region R is rotated around. Now, again, this kind of looks a little messy, so let me just break it down by a single cross section, and maybe you'll see why we call this the washer method. Let me go back and erase these words so we have some more space. Okay, so let me just take, let's take this point right here, and I'm going to rotate that around. So that would be a slice of my big cylinder. And then I'm going to look at this point directly underneath it, but that's on the blue curve. And I'm going to rotate that around. So you can see what develops is what we call this washer type figure. And if you've ever, built something, maybe if you've ever worked in construction, you've probably worked with these. From my experience, they go over a bolt or maybe a screw to kind of hold it better in place. But essentially, it's a flat disc with a hole taken out of the center. Let me just show you a picture of what an actual one looks like in real life so you can see the resemblance. But they're these flat discs with holes in the center. And the hole in the center could be bigger or smaller depending on, how big you need your washer to be. That's why this method's called the washer method, because our individual slices are discs with holes in the center. So let's go back here. And again, I could draw a few more slices for you, but again, it looks pretty complicated because you have a couple different circles for each individual slice. Let's just talk about how we would find the volume of one of these slices. Okay, so essentially a disc with a hole cut out from the center. So the volume of the blue, again, that solid that's made up of the larger red disc minus the smaller green disc, the volume of the blue is going to be equal to the volume of the red minus the volume of the green. So the volume of the red, that's still going to be pi r squared times h. Now, the height of the red and the green, they're both going to be dx, right? They're going to have the same height. The radius, though, is going to be different, right? The radius of the red is not going to be the same as the radius of the green. So what we're going to do is call these R1 and R2 just to differentiate. Okay, if we look at what the radius of the red is, well, the radius of the red is the difference or the distance between the purple horizontal line and the x-axis. In this case, because that purple line is horizontal, right, the distance is always going to be the same. The distance is going to be 4. So our R1 is 4. Our height is dx. For the green, our radius, or r sub 2, is the distance between the blue curve and the x-axis. Now this is changing, right, because the blue curve is not always horizontal. But it's just going to be the y value of that blue curve, which is x squared. And our height, again, is going to be dx. So again, if I do some simplifying here, I end up getting 16 pi dx minus x to the 4th pi dx. And if I simplify one more time, or rather I can factor out my pi from both, I get pi times the quantity 16 minus x to the 4th. And I can actually factor out the dx as well. So this represents the volume of just one of those. Again, in this case, it's not a disc, it's a washer, because there's been something cut out from the center. Well, if I want to find the entire volume of the entire solid, if I sum up all the volumes of those washers, I just need to integrate. Let's do that over here. It's the volume of the whole. I'll just say the volume of the solid. It's going to be equal to the integral from 0 to 2 of pi times a quantity 16 minus x to the fourth dx. And then we could go through and integrate that by hand. One other kind of representation I want to show you, or another way to set up this integral. And let me get rid of this. You can always pause the video and go back and look at that if you want to. Is you can actually think about this as two integrals. Oops. Remember how I said that this volume was essentially a big cylinder minus the volume of this little top portion. And maybe let me draw that on the graph again. This video might go a little long, but I think it's important to understand the visuals here. So if I revolve that purple line around the x-axis from 0 to 2, I end up getting this red cylinder. We know that doesn't represent the area of R. But now, if I also revolve the blue curve around the x-axis, I get this top-looking figure. So the way we can also think about this is, right, take the whole, take the entire cylinder. We could write an integral for that. Let's do that in red. So the volume of the red cylinder would be the integral from 0 to 2 of pi. The radius of the cylinder is going to stay the same, right? That's 4 for every little disk, dx. Then we could subtract out the volume of the top, right? And the radius of the top being the value of the function. So x squared to the power of 2 dx. Okay, so the volume of the entire red cylinder minus the volume of the blue top would give us the leftover volume, which would be the volume when R is rotated around the x-axis. So the relationship here, if I subtract these two integrals using integral properties, I get this black integral. Now, it's up to you, right? If you feel like internally you need to write out the red and the blue integral first to kind of make sense of what's going on and then combine them into one integral, fine, no problem. I would rather have you do that than just try to memorize, what the black integral looks like for this diagram, right? I'd rather understand that we're taking the volume of something larger, subtracting out the volume of something smaller to get the volume that we need. But it turns out if you simplify the red and the blue integrals together, you do end up getting the black. Okay, I actually am not going to take time to go through and find the area here by hand. I will just tell you what it is for time's sake in the video. You should get exactly 128 pi over 5, though. That would be the volume when you simplify and evaluate, or evaluate and simplify. I do want to do at least one more example, though. So let's get rid of this. And let's do an example where we revolve around the y-axis. Going right here. Okay. So it says region R is enclosed by the positive x-axis, the curve y equals x squared, and the line x equals 2. What is the volume of the solid generated when R is rotated about the y-axis? Well, if it's being rotated about the y-axis, that's a giveaway that our integral needs to be in terms of y rather than x. It says give the exact answer in terms of pi, so this one would be completely by hand as well. Okay. So let's try to visualize what's going on here again. Maybe you want to pause the video and try to sketch what this looks like on your own. Again, the more you explore on your own rather than listen, it's probably going to solidify better inside of your head. But essentially what's going to happen, to figure out the volume when R is rotated around, we're actually going to have this large cylinder. I'm just going to draw the two bases of it. Actually, this line, this curve did not need to be dashed. So we have the cylinder, and then we're going to be subtracting out the volume of this blue dome-shaped figure. So you'll see what that looks like in a second. I'm going to learn my lesson. I did this incorrectly the first time and had to do a redo on this part of the video. So again, we get this blue dome-shaped, this blue dome-shaped figure that we're subtracting out of the red figure. And it's this green solid that represents what we would get when we revolve R around the y-axis. So we have the large red cylinder. We're subtracting out the blue upside-down dome, or this little bowl-shaped figure, to get the green solid. Now, I'm going to erase this and just, again, visualize what one cross-section looks like. In this case, what a washer looks like. So let's go back to the red. Let's do it about right here. It looks about the same distance away. Let's do blue from the blue curve. Okay, so again, to form that green solid, we would have this green washer. And if we summed up all the volumes of these green washers, we would get the volume of the green solid. So again, a couple ways you can think about this. You can just, you can try to write this as one integral. I tend to think it makes more sense to try to write them as two separate ones and then combine them at the end. So that's what I'm going to do. I'm going to look at the volume of the red cylinder by summing up the volumes of all the red disks. So the volume of one red disk would be pi r squared times h. We'll actually call this R1. It's going to be different than the blue. Now the radius here is the distance between the vertical line x equals 2 and the y-axis. That distance is always going to be 2. So it's just going to be 2 squared. The width of these washers is going to be dy. Everything's in terms of y. So the volume of one of these red disks is going to be 4 pi dy. The volume of the blue disk, pi, we'll say r sub 2 squared times h. Now, the radius here, that is the distance between the blue curve and the y-axis. The problem is our function is currently in terms of x. We want it to be in terms of y. So we just have to solve for x here. Y equals x squared. Square root both sides. I get x is equal to plus or minus the square root of y. We are only in the first quadrant, so I only need to worry about the positive root. So I'm going to rewrite my function as x is equal to the square root of y. So my radius is just going to be the square root of y. So I get the square root of y squared dy I simplify here. I get pi y dy. So if I wanted to figure out the volume of the red cylinder, I would sum up all of the red disks. Here I'm going from 0 to 4 on the y-axis. So 4 pi dy. If I wanted the volume of that little upside down dome or the bowl, I'd be summing up all of the blue disks. Same interval, so 0 to 4, of pi y dy. Now, if I want the volume of the green solid, right, which would actually be stacking those green washers on top of each other, well, that's going to be equal to the volume of all the red disks summed together, so 0 to 4, 4 pi, minus, sorry, let's not forget our dy. You know what? Let's color coordinate this. A little OCD, but that's okay. So the volume of the green solid is the volume of the red minus the volume of the blue. Now we could combine that, right? And we will do that. And you could pause the video and think about the algebra there, but all I did was subtract the integrals together using integral properties. You're able to factor out the pi and the dy. That looks a little bit like a dx. Hope I didn't say dx. Should be dy. Factor out the pi and the dy from both of those, and then you're just left with 4 minus pi. Again, I'm not worried, but my concern is that you understand the setup. I know we can evaluate an integral like that, but the important thing is understanding how we get there. Okay, let's finish this video off by evaluating. We didn't do the last one, so we'll go ahead and do this one by hand. Let me do some erasing. Give us some space. I'm going to evaluate the black integral. So that's going to be the easiest, rather than doing 2 and then combining. We can get rid of this. First thing I'm going to do is just pull the pi outside of the integral. If I take the antiderivative, I'm going to get 4y minus 1/2 y squared, evaluating from 0 to 4. It's going to give me 16 minus 1/2 times 16. And if I substitute in 0 there, I'm just going to get zeros. You can write that if you want, it doesn't matter. So that gives me pi times 16 minus 8, which gives me 8 pi. So the volume of the green solid would be 8 pi. Okay, that will do it for this video. We will have one more lesson where we revolve these regions around some other axis rather than the x or the y. So it does complicate it a little bit more. But again, you'll see the similarities between this lesson and our previous lessons when we do it. As always, enjoy the rest of your day, and we will look forward to seeing you next time.